Maybe we can do a recalling session and bring up these equations, but for you, you can just flip over your notes if you are taking them and see this equation. So moving linearly, expanding, taking more and more space, probably. And we may want to play true scientists or be a true scientist. So expand is too vague. We can tell like size of electron, or maybe the half heights, widths, same like one perspective, or threshold. If the probability is bigger than 1%, we discuss it, we debate it as radius of our squeezed electron. So you can assign this letter sigma as a size of a space occupied by electron. And then our science can be targeted to find dependence on this as function of time. Okay. It is very good formulation of a problem. It is something that our skills would allow us to do. There will be a little effort, but it is a good problem. I promise we will solve it. So, how are we going to start? And by the way, here is the answer. It's you can look on it so that it will be a proof that there is an answer. But right now, it doesn't tell us much, and our main goal is not to address this rather primitive problem, but develop methodology, protocol, how to get to this answer. So it's not a big deal. Here, it will be position minus initial position minus momentum or mass times t. Under this, here will be a square Gaussian function, and in the denominator, the width parameter will grow quadratic. Someone is late by half an hour. I did this when I was So, how do we get to this answer? Guess what we are going to do. So we were recalling our arsenal of skills, not just to entertain ourselves or torture ourselves. It was intentional. So we need to predict the future. Right? We need to go from past to the future. Our past is squeezed electron. Our future is unknown electron. So we need the initial condition, which will be wave function x and t equals 0. And by the way, another approximation. Let's consider that our universe is one dimension. Because 3 dimensions is too much for us. Let's do baby steps. And we need to go to the future, which will be psi of x over t equal to 0. For interpretations later, after we get this wave function, we want to take the absolute value square. But first, we need to go from past to the future. So, in order to go from past to the future, what do we do? What is our protocol? You were contributing enough. I will speak. Yeah. So our future is a summation of all eigenfunctions. By the way, eigenfunctions. We'll discuss on the next slide.
A wave function?
Huh?
A wave function?
No. Wave function which is the same as eigenfunction of what? Of which operator?
Okay.
You cannot be wrong telling eigenfunction of Hamiltonian. You can, in 99.9% you will be correct. But which Hamiltonian? So you need a Hamiltonian of electron in vacuum. Then we need energies of electron in vacuum. And then some expansion coefficients. So basically we need to, which will depend on the past, on initial condition. So basically we need to fill these three components and then perform this summation. And then we will get the answer. And everyone, especially me, will become happy. This is the plan. How are we doing this time? 5, 10, 15?
It's 11:35 right now.
Okay, so, oh, that's generous. We have about 15 minutes. We can progress substantially on this plan, but this is something you may put down in your records. It will take us more than today's meeting to go through this plan. So fill each component of this expression and perform summation. And then we will get answer which will prove right or wrong the hypothesis of expanding electron. Okay? Wave functions of what? Which functions and of which operator? We do not behave rigorously as people do in math. We do little experiments. And we do not know much functions that we are familiar with. Let's repeat a simple mathematical experiment and then do a wow moment and oh, it's an answer for this question. So we do have two pieces of knowledge in our baggage. First, that kinetic energy is equal to what? Energy of motion.
NV squared.
And if we do not have velocity but have momentum, V equals P divided by M, right? Because P is equal to mv. So how do we convert it? If you replace V by P over M.
P squared over 2M.
Excellent. If there are no ions, if the spatial electron is free, it has only kinetic energy, right? There are no potential energy. On the other hand, we are approaching tricks of quantum theory, so we do not write just P like simple. We always want to add hat on top. So what is the momentum operator?
So negative.
It's the only thing that you need to memorize. The rest we will derive.
Negative I equal R derivative of spatial dynamics.
Okay. So how do we form P squared over 2M? It's just having this operator and take it squared. So I times I will be minus 1. Minus 1 times minus 1 will be 1. So just plus. per square 2m d2 d square. So we set up first Hamiltonian in your life. You derived a Hamiltonian of free electron in the vacuum. Now, for our prescription protocol, we need to know eigenfunctions and eigenenergies of this Hamiltonian. We need to place something here, there, and there. Functions, phase accumulations due to eigenenergies, and expansion coefficient. So, to get these energies and functions, we need to solve stationary Schrödinger equation. And in whatever follows in the course, we will solve such equations. But now we will just guess the solution and obtain a positive surprise that a guess solution will match this equation, just to save time and because everything is set up in a simple way. H equals minus d plus 2 d squared. Why don't we try our favorite function and check whether it will help us to solve this equation? So we can call it math experiment. Try e to the power minus I p. Instead of k, we can use p like h bar to dimensions. H prime dx minus so we keep the constant and first derivative of the last derivative unchanged and take this derivative. What are we getting? The minus all factors come up front and the function stays unchanged. E to the power minus I dx. Right? Now this factor can migrate to the front and taking derivative once again. So we get this factor minus I once again, and the function stays unchanged. Minus I, right? Take the first derivative, the second derivative. Then we multiply this factor. Minus times minus will be plus, and I times I will be there should be. I was so excited that I already made an error.
Should there also be a coefficient in front of the exponential?
Yes, but we will die if you protest the coefficient. There should be normalization. So it's minus, and then you have one more minus because of multiplication of imaginary units. Then h bar squared over 2m squared e to the power minus I ax. So here this two minuses compensate, and we will get h bar squared k squared m times the function we started from. So what did we do? What did we came through? We take a guess function and we checked whether it will be a solution of the eigenvalue problem. So we applied Hamiltonian to this function and realized, what a surprise, the function hasn't been changed. Through application of the differential operator, we obtained some factor up front, which we can interpret as energy. But the function didn't change. It was oscillator exponential and it is oscillator exponential. Good. And the P times H is momentum. So this expression here, H bar square K squared over 2m, is actually P squared by 2m. So coincides with what we may want to have. But here the P is not an operator, but the eigenvalue of the operator. It's number, not an operator. So we built Hamiltonian. We didn't set up initial condition that we should do. And our output in our exercise will be to find the function and then construct probability distribution. So we already have solution of stationary state eigenvalue problem in the yes. So for our protocol, we already have something to fill inside the red box and green box. Okay? So instead of this phi over k, we will put in e minus I. Ax, and instead of e sub k, we will put h bar squared is equal to 2m. So we are 66% done. Now we need to find expansion coefficients. So in order to find expansion coefficients, we need to set up initial condition. So here is the moment of creativity. Instead of doing boring math, we can design initial condition, anything we like. You did agree that in our scientific approach, we want to start with squeezed evacuum. So why don't you try to describe initial function for the squeezed evacuum according to Dr. Gauss. So let's now sit in the vicinity of some initial position and it has some width. So in our one-dimensional space, we have a bigger probability to find it near x, sub-zero, and less probability apart from it. Objections? Okay. So let's call it x, comma, 0, or time equals 0. And now we need to plug this initial condition into our recipe of obtaining expansion coefficients, C sub t. We do know the functions, which are exponentials. We do know our initial condition. And we know how to integrate. So if we perform this operation, we will have C sub k that we can plug into our recipe. So this question is a part of the homework. When we meet in lecture class on Friday, I will assume that you know the answer. I will just use the answer and not without showing you the path how to get it. Today we are meeting at which time? 5 downstairs this building. And where should we go?
1:32.
1:32, yes. I have the nicest possible slide that everyone will enjoy. So, meeting is dismissed. Looking forward to see you today at 5. We'll stay here to answer any questions in terms of
Yeah.
I'm not assigning homework. I can give you the